Alright, I'm starting the stream. Whatever that means. Not that I know. Adam's not here. Maybe Adam's streaming. You guys got 6 more sessions after this, so your Saturdays are almost free again. Very close.
My wife finally said to me, like, we haven't done anything on a Saturday for a really long time. And I said, yeah, you got less than a month left, and we'll do something one of these Saturdays.
We have 2 more Saturdays after this. 2 more. So we have next Saturday's Daniel, and then it's me, and then we're done. After that, it's over. Alright, I'm gonna start class. Whatever that means today. Data structures. You got it. So we're gonna go over, literally today is all slides. Woo! There are some exercises that are in there that you can look at, like, hey, guess the big O notation on this, guess what data structure should be good here. Just do them if you want to. You can look at those. The solution's already uploaded to GitLab, so you can look at them and try to do that if you're interested in continuing to learn these things, which, again, I've told my class, I do recommend you learn these things. I'm not going to be able to teach you really anything today. I can kind of get you introduced to it, and then it's up to you to move forward. With that in mind, a couple of really good books on data structures and algorithms. This is the one that I actually used along with the Coursera class that Robert Sedgwick, the guy who wrote the book, teaches. It's free. It's from Princeton. It's really tough, but it teaches you a ton of good stuff about big O notation, the best data structures to use for very common algorithms, and stuff like that. Time and space complexity really makes you think. And then another one that's supposed to be really good that I haven't had a chance to look at is this one. These are obviously in the Saturday channel. These books are expensive because they're effectively textbooks, but they're good books, and having one of them on your shelf somewhere that you can refer to or to be able to go through is totally worthwhile. If you want a general purpose one, I would recommend you go with the second algorithms book, the Introduction to Algorithms, because it's more encompassing than the one I sent out that I said I used. That one has a very specific set of algorithms in it. It's a great place to get started and teaches you the basics, like I think there's some linked list stuff in there, there's map stuff in there, and then there's a bunch of disjointed unions and all kinds of other things, that graph traversals that you probably won't use that often. But linked lists and maps you probably will use, so it's good to understand what they're good for. Okay, so with that in mind, I was thinking about it when I was looking at this slide deck. I don't know when deliverable 2 is supposed to be due. I actually don't even remember what's on deliverable 2, so I gotta look up that and figure that out for you guys. And talk to Daniel, see when he wants his class to have it due, because we'll probably stagger. So if any of the TAs can find the deliverable 2 information and Slack it to me, that'd be fantastic. Anyway, computer science, data structures, and algorithms. So first things first, we'll do a project check-in. We'll talk a little bit about computer science and what it means. We'll talk about Big O, and then some common data structures that you'll run into and, kind of what they mean. So, project status. Fist of 5, how are projects going so far for everyone? 4s, 5s, 4s, 5s. That's good. I'm seeing generally 4s and 5s, so that's good. That's how it should be. If you have less than a 4 or 5 and your group as a whole feels that way, let me know. Let one of the TAs know. Let Daniel know, so we can kind of help you in whatever rut you might be stuck in. If it's a personnel problem, it's a little bit more sensitive. We'll deal with that one privately. But, yeah, it's good that everyone's kind of doing well. So, supposedly, deliverable 1 was due today. That's not true. We already did that. Computer science context. Alright, so the computer science fundamentals. the computer science stuff is vastly different than what we've been doing this this whole cohort. This cohort's really been about software development, right? And learning the web tech stack and the MERN stack and all that fun stuff. So while we've taught you a lot about software development and how to learn these technologies, we haven't taught you really anything about computer science until this week, right? We talked a little bit about, search algorithms. We talked a little bit about some data structures, sorting algorithms, stuff like that, right? So these concepts, they're very fundamental. They're not easy, regardless of them being fundamental or not. And your takeaway from today really should be to understand that there is a way to measure efficiency and complexity in an algorithm, and knowing those things is pretty good for solving certain problems, right? And you should have a general understanding of what that means, how to measure efficiency and complexity. And you should have a general idea. You shouldn't know exactly how to calculate it, and if you do, great, but you should have a general idea of what we're talking about. So does anyone remember? I don't even know what the Stokes theorem is, so clearly I don't remember it. But mathematical stuff is hard to remember, especially as we get into our careers and we get out of school. The last math class I took was like 8 or 9 years ago. So when it comes to calculus or whatever, I don't remember anything about it at all. But it has not affected me at all, so it's great. However, data structures and algorithms do have sort of a mathematical feel to them. They aren't totally mathematical. I mean, they are. They're algorithms. There's some math behind them. But you can kind of, if you understand how to read them and you understand how to kind of deduce the complexity of an algorithm based off the code you see, it's not super concrete math. It's more of kind of a gut feel, but here's the math behind it, if that makes sense. But they get kind of crazy. The code gets kind of wacky. As I told my class, we strive to write readable, very maintainable code always in every scenario, and sometimes with these very complex algorithms that we use for specific efficiencies and specific scenarios, there's really no way to write the logic in a way that's both effective and easy to understand first pass, right? Sometimes they're just dense. If you want to write the code the most efficient way, sometimes it's just dense and there's no way around it. You have to read through the code a lot, you have to debug the code a lot, and you have to really play with it before you totally understand what the algorithm is doing and why it is even efficient, right? And that's kind of computer science in a nutshell, is like, how do we find these algorithms? How do we deal with them? How do we find the most effective way to write this code? And, a lot of computer scientists, speaking from a very generalizing a lot, and, obviously this is a fallacy, but a lot of them seem to overcomplicate things, in my opinion. May or may not be true, but I don't know. Computer science degrees generally don't teach you how to write efficient. They don't teach you how to write maintainable software and do it in a professional sense. They teach you how to write efficient algorithms. So they're very different problems, actually. One of the things that we'll talk about is I suffered from imposter syndrome for a long, long time because I don't have a CS degree. I don't know. Is there anyone in here who has a CS degree that's like going through the course as an extra augmentation of that? I've had students that have before. Yeah, you do?
Yeah.
Yeah, so you have a CS degree, so you've seen some of this stuff before, but a lot of us don't. And the imposter syndrome, even for you, might hit you every now and then. It just, you feel like you don't belong sometimes when you're writing code, right? I didn't get a CS degree. I don't understand necessarily, how to do a graph traversal off the top of my head. You should not remember that, okay? If you do, you're either an ultra nerd who loves algorithms, which is totally cool. Don't get me wrong, I am too. Or you do that every day, right? That's kind of it. Otherwise, you don't need to remember that stuff to be a great developer. You really don't. So be wary of the imposter syndrome. It is very easy to let this slip into your mindset and go, I'm not good enough to do this. This is way out of my league or whatever. And that's just generally not true. There's a lot of really bad developers who've gotten really far in their career. Let me tell you. Okay, so why cover this? The most important reason for you all why we should cover this is interviews. You're going to see this kind of stuff in your interviews. I'm sure some of you already have seen this kind of stuff in your interviews. What is the efficiency, or what's the big O notation, the time complexity of this algorithm, or how do you find constant time, reference checks or something like that? I don't know. Right? You might see, how do you reverse a linked list? How do you deduplicate a linked list? Stuff like that. You might see it in interviews. You just might. So knowing what's coming and being able to study that more effectively is very helpful. If you do get into a large code base and someone says, hey, you need to optimize this, it's a little easier to think in Big O sometimes. I would say with most optimization in general business class software, it's going to come with database queries and optimization in terms of like inter-process communication more than it will Big O. But every now and then Big O comes into play. Sometimes it's just pure sloppy code in business apps that you need to clean up. But Big O does come into play. And then also it'll help deepen your understanding of software in general. So again, I'm going to teach you the terminology and some of the basic concepts. I'm not going to teach you the in-depth Big O notation, how to calculate it in all scenarios. I'm no expert. I know the gist, right? I know, hey, you know, we might want to use a dictionary here because at worst case scenario, it's going to be a linear lookup time, right? For something, you know, but best case scenario, it's 01, right? So I might know those things, but I'm no expert. If you want to go deeper, these are some books you can look in. The books that I select out to you, I think, are a little better for general algorithms than these are. These are going to be about, they're going to have the JavaScript flavor, though, so it'll be a little easier to understand, probably. And these, I've not read either of these books, so I can't speak to whether or not they're good or whether or not they'll teach you effectively. They probably will. But those books are like the de facto, like, hey, you want to learn algorithms? These two books will get you there. And they're hard books. All right, so efficiency. What does efficiency mean in software? Effectively, it's the number of steps it takes to complete an algorithm. That's really what you can boil it down to. If you have more sets or more instructions, more lines of code, sometimes that means it's less efficient. More lines of code doesn't always translate to that, but it could. If you have fewer steps, generally it's more efficient, right? It's a generalization again, but it's more or less true. So what is a step, quote unquote? Sometimes it's an instruction, so a line of code. Sometimes can be considered a step, maybe a loop. An iteration in a loop could be considered a step. Accessing something in an array can be considered a step. There's lots of ways that you can consider something a step. Some of them matter more than others, as we'll see. But basically any sort of instruction that you would give your language to execute, you can consider a step in your algorithm. So again, fewer steps sometimes equates to faster code. Generally speaking, if you have two pieces of code that do effectively the same thing, one has fewer lines of code, assuming that there's not any underlying, you know, functions you're calling or whatever, the fewer steps will be faster code or more efficient code, right? So here's a quick question. Which one of these is more efficient? And which one has fewer instructions? There's this list items function that loops over an entire list, and there's this head function that just takes the first element of a list. Which one is technically more efficient? Number two, the head function. The head function technically is more efficient because it has one instruction, right? It just takes the first element. Granted, these are two totally different algorithms that do nothing similar at all, so comparing them is kind of dumb, but technically, the second one is more efficient because there are fewer steps there. It's constant time. It's just, boom, we need the first element, that's it, we're done, right? One instruction. Whereas the other one is totally dependent on how long the list is. So if you have one item in your list, then they're the same efficiency. The first one is 1, the second one is 1. If you have 2 items, well, now that first list items function is twice as many instructions as the first one, so it's less efficient, or it takes less time to run. I don't know if efficiency is really the question here, or just how long it takes to run, right? So it takes twice as long, maybe even longer, because you have this I assignment, and then you have this condition on checking the list length, which that computation could be a more expensive one than you'd think, depending on how it's implemented under the hood. Then you have to increment the I. Like, there's a lot more going on in this one than there is in this one, and it could end up actually being far less efficient based on how many instructions are actually generated by the interpreter and then the just-in-time compilation system. Alright, so again, the list items function is theoretically n instructions long, right? For how n is how many items are in the list. And you'll see this notation, O of n, linear, time complexity, big O of n, right? So n represents how many items are in whatever it is you're trying to do. So, time complexity. That head function always executes one instruction no matter how long the array is. In theory, that is the most efficient any algorithm can get, is no matter the size of whatever you're operating on in your algorithm, it takes constant time, one operation, to do whatever it is you're trying to do. That is the most efficient algorithm that exists in the universe, is something like that, right? And it's not possible to get this constant time algorithm for everything, right? Or this constant time for every algorithm, right? Some of it is just we haven't found a way to do it, or is impossible based off of the current way that software even works, that computers even work. So how do we quantify efficiency? Well, look, we have an array here with 3 different names. We could potentially generate an array with 1,000 elements. And if we ran head on both of those, the array with 3 and the array with 1,000, it would take just the same amount of time in either one to get the first element, right? That's how you can quantify that efficiency. That's that O constant time. You'll see it O parentheses 1 is what it'll look like when you're reading it on paper or whatever. That's that constant time lookup. Doesn't matter how large this array is. We could put 100 million items in that array. It's still going to take one instruction to get the first element out. But then if we had this list items function and we had an array with 3 different elements, an array with 100 million elements, the 100 million is going to take a whole lot longer than the 3. So longer arrays end up taking more time at the end of the day. Double the array length, you double the time it takes. Triple the array length, you triple the time it takes. So on and so forth, right? Pretty straightforward at that point with the linear time complexity, that O of n that we're seeing so far. All right, so what does this basically mean? You'll often hear it called the running time of the head function, and the list items, they scale differently, right? So the time complexity, the running time, there's a different scale, different factor related to how they change. The time complexity is the rate at which an algorithm slows down as the input grows. That's what this big O notation that I've alluded to that we're going to talk about today stands for. It's this time. There is a big O for space complexity too, but I don't know if we talked about that. Head is always one instruction. Again, running does not slow for larger inputs. And the running time is constant. The time complexity is O of 1, constant time. It's always one instruction, right? Say it again. List item takes n instructions. The running time depends on the size of the array. Double the array length, double the time. The running time increases linearly with the array length. So we have linear big O notation, linear time complexity. So now we're actually going to show big O notation so you can see it. But any questions at this point? Everyone with me? Fist of 5. Nice. Okay, people feeling pretty good. That's good. Okay, so what does big O actually look like? Big O lets us describe how the running time scales based off the input size, right? So it is the representation in algorithmic terms of that time complexity. It's denoted with a big O, literally the letter O, which is our growth factor. The O stands for the worst case scenario, generally. There's different ways, the different types of algorithms. There's a best case, an average case, and a worst case. Big O is the one we like to use because it's the worst case scenario. And we generally compare that worst case scenario, right? So something's worst case is 1, constant time. Something's worst case is linear, O of n, and they do the exact same thing. Which one are you naturally going to use? The constant time, right? It is magnitudes more efficient depending on the size of that array. Now, it could be the same efficiency if that array is one item, but generally speaking, when you have small arrays of one item, you don't really care how long the algorithm takes because it's one thing, right? So in real scenarios, this big O means a little bit less depending on the potential size of that input, but we'll talk about that too. So this is how we would notate it. O of 1 is that head function, constant time. O of n is that list items, linear time based off of the input of the array, right? Does this make sense to everyone? There are big O classes. Okay, so what is this? Can anyone tell me, who hasn't done computer science before, what the potential time complexity for this function would be? So this one's a bit tricky, but if we look carefully, we can see that it's not only dependent on the length of the list, because we're iterating through the list, but it's depending on the length of the list twice. Because every time we iterate through that array, we're iterating through it completely again, which means the time complexity is going to be the length of the array times the length of the array, right? So the time complexity is O of n squared, which is called quadratic complexity, and is one of the worst complexities you can come across, but it happens. So an easier way to calculate this is if we have 2 elements in the array, it's going to take 4 times the amount of time than if we just had a linear equation, right? If we have 3 times the length of the array, it's going to take 9 times. Basically, it's n squared, right? N times the length is n times n times longer it takes to go through the function, so O of n squared. The running time grows as a square of the input, the quadratic time complexity, right? And it's denoted like this. O with an n squared. It's not a particularly efficient algorithm when you see that quadratic time complexity. A good rule of thumb is when you see something that's quadratic time complexity or higher, you try to optimize for something less than that, because this quadratic time complexity is a real killer. And there are some algorithms that we haven't gotten any better than that. There are some that are even worse than that. And the only way for us to run these algorithms over large sets of data is with big data farms and stuff like that, and gigantic mainframes. And sometimes that's all we can do right now. Sometimes we can find a better algorithm for doing it. So your selection sort, your insertion sort, this is their worst case scenario, because they effectively have to go over the entire array twice, right? Once they have to go through it, and every time they go through that array to find something to move in that array, to swap, right? They have to go through it again to find the other pair that they might have to swap with in both of those. That quick sort has a worst case scenario of O(n) squared. However, its best case scenario is much better, and that's why we actually end up using it. So an important thing to note is if you have a loop inside of a loop and they're iterating over the same array, you have an n squared operation, and that's generally bad. So one thing you'll hear a lot is pre-optimization is evil, right? You don't want to optimize your code before you even know it's inefficient, which is true. If you haven't timed your code to know that it takes a long time to do something, there's no reason to spend the time trying to optimize it. However, if there's an easy way to get around doing nested loops, you should, because it's generally not a good thing. Now, granted, if your array that you're iterating over is only 4 items and it never gets bigger than 4 items, it doesn't matter. It's going to be so fast, who cares? 16 operations is going to be trivially small for a computer, so it's cool. But if you can't guarantee the size of that array, and that array is going to come in at 1 million items potentially, it's going to take a long time, might never finish. So you should avoid that, right? But that's only if you know an easy way to do it that doesn't take any more time than just writing the 2 loops, right? And once you get a little bit better with writing code, you'll be able to see these a little bit easier, and you'll go, oh, I have a nested loop, I can easily replace it with a map or something like that, right? And you can kind of come up with easy solutions to get around that. 3 nested loops, for that matter, is going to be n cubed, even worse. That's a horrible, horrible runtime for a function. 4 nested loops is n to the 4th power, right? That's just god-awful. Why would you do that? So here's another interesting one. We looked a little bit at the binary search algorithm. Does anyone know off the top of their head how fast a binary search is? What's the time complexity of a binary search? And log of n?
Log of n.
And log of n, why?
Because every single time you traverse a node, you're cutting down the amount that you have to traverse it by half.
Yes. So this is tricky because it looks like you'd have to iterate over everything potentially to find something. Let's say we're searching for the 7, right here, right? So the way binary search works is we're not going through the entire list of items, because this could be represented by an array. Effectively, this tree could right here. We would start at 8, which is either the first one or the middle or whatever, depending on how you structure the array. And then if we wanted to find 3, for instance, we know that 3 is smaller than 8, and so we go, okay, great. We just need to go to the left of the 8, and then we've found the 3. However that's implemented, right? So as opposed to starting at the 8, or starting even at the 1 and going all the way through, you could just immediately go from 8 to 3, because 8 is less than 3. Now, if we're looking for the 7, we only have 4 operations that we have, 3 operations we have to do, right? We start at the 8, we go, okay, 7. 7's less than 8, so we're going to go to the left of 8, which is 3. 7's bigger than 3, we're going to go to the right of 3, which is 6. 7's bigger than 6, we're going to go to the right of 6, which happens to be 7, right? As opposed to looping through the entire thing to find the one that potentially matches. So, is it O of 1, O of n, or O of n squared, or something else? It's O of log n, and this is why. So the binary search this array by hand for 3, then 9. Count the steps. Okay, so if we're going to binary search it, say we started at just 5, for instance, because that's the middle. If we were searching for 3, we would say, okay, well, is 3 bigger or less than 5? 3 is less than, so we could go to the left of it, potentially. Or we could divide 5 by 2 and see whatever the index is on the left-hand side, which would take us to 2, and then we could say, hey, is 3 bigger than 2? It is, so we can go to the right-hand side of 2, and then we can kind of deduce, eventually, through 3 operations, potentially, how long it's going to take to get there. Binary searches are important to note because they really only work on ordered sets, and your set becomes ordered as soon as it enters the tree, because the tree sorts it in such a way. So this array could represent a binary tree with the root at 5, because when you enter, when you have like the base index or whatever, or your base node index, it will tell you where to start in the tree. So it takes 3 steps. It's much faster than linear time, so I don't know what these are saying. Anyway, it's log n time because of how you traverse through that tree, right? So go to the left, go to the right, so on and so forth. All right, so log n. How many times do I divide n by 2 to get 1? Anyone? What is log 8? What is the log of 8? Does anyone know that? I don't know that either. 8 divided by 2 equals 4. 4 divided by 2 equals 2. And 2 divided by 2 equals 1, so 3. So that's kind of a way that we can see how this logarithmic equation works. So log 8 equals 3. I don't know how to generally calculate logarithmic times. Here's how I look at logarithmic equations from my point of view. So basically, if you can see that there's not a linear representation of the data structure, right? So we have a tree, or we have a binary search, and we're going through it, and we're using some sort of method to kind of skip certain elements, as opposed to going through the entire thing. You can sort of deduce it's going to be logarithmic because it's not going to take as many iterations as the array is in length to get through the entire search or through the entire algorithm. The concrete math isn't always so important in deducing it. Sometimes it is, depending on what you're doing. What's more important is that you know the gist of how how long the algorithm is going to take to execute. So if you happen to know that log n, which we now know is faster and more efficient than a linear time algorithm, you can easily deduce that if there's a similar algorithm for log n versus a similar algorithm for linear time that both work in the same way and get you the same final result, you should use the log n algorithm. That's what's more important, I think, than calculating out the logarithmic time, the log of n. Again, don't really worry about it. So the head algorithm is O of 1 at constant time. No matter how large that array is, it's always going to take one operation. The list items is O of n, so it depends totally on the length of the list, and as the list grows, so does the time complexity of that, or so does the time it takes to execute that algorithm. Finding duplicates was an O of n squared, So you had to loop through the array, and then every time you loop through the array, you had to loop through the array again to try to find a duplicate. So you have this equation where for every element in the array, it grows by a factor of itself, right? That's how long it takes to execute this equation. And then for log n, the input size is effectively cut in half every time you go through an iteration of the algorithm. So you can kind of view it that way. And that's just, these are very general time complexities that you'll see, and they're usually the ones you see. There's a couple others, n log n. There's like a log star n, and then there's some 2 to the n, stuff like that. But these are some good ones to know about. And this is kind of what their graphs look like too. If you wanted to compare them on a graph of time versus size, you can see right here, this gray one, the O1 is just flat. It always takes the same amount of time. The log n is a nice curve here, where it starts out taking almost effectively as long as a linear one or a constant time one. It actually takes longer than a linear one for a little while, but then as the input get larger and larger, that logarithmic function ends up, you know, cutting down the time it's actually going to take to get through an algorithm, and you find yourself kind of not too far away from that constant time, right? It's still going to take longer than constant time always, because it's not 1, but it's fairly efficient as far as things go. There's like an the square root of n, which is a little worse than the log n. As you can see, again, the efficiency doesn't pick up above linear until you get into larger sizes, right? Larger input sizes. So, again, one of the students on Monday, Wednesday was asking, hey, is there a reason why we use, say, selection sort over quick sort? Well, yes, there is, because you can see the quick sort's best case scenario is going to be log n or n log n, something like that. And the logarithmic time complexity is going to take a little bit. It's going to take a certain size of elements before it's actually more efficient than the linear time. Or even the quadratic time, right? So that O(n) squared, the log n still takes a few elements before it beats the quadratic time. So if you have a really small set, like say 10 or 7 elements or something, you might as well just do a really simple algorithm to just get it done, because it doesn't matter. N3 and then n to the n are like some of the worst time complexities you can run into, right? So n cubed right there, for every time you iterate through an element, you're going to iterate through that array again, and then for every one of those iterations, you're going to iterate through it again, right? And then n to the n is for every element, you're going to iterate through the array that many number of element times again. So you can see how this scales, the time complexity scales. And again, these things aren't super important for you to memorize right now. It's just good to get a gist. Like I said, I'm not an expert. I don't know necessarily how to calculate all of these mathematically, nor do I really care. What I care about is what are the general data structures and algorithms related to these time complexities? When are they useful? How would I use them, right? And if I really needed to deduce the time complexity, I can get a rough estimate looking at the code. It's not going to be perfect, but it'll be good enough to let me know, hey, is there a way that I can make this subsection more efficient, right? And that's what you want to do. Okay, so is everyone with me on the big O notation and kind of what it means and how you use it? Fist of 5? Thumbs up are good too? Yeah. Okay. All right, if you have more questions on the big O, we can go over it more later. Ask any of the TAs, we'll help you best we can. Yeah. So some common data structures. What is a data structure and what is an example? Before we answer that, we're going to kind of talk about how memory is saved in the computer. Okay, so a memory gets saved in RAM. That's awesome. So what does RAM look like? Well, technically it looks like this. Technically it looks like this, little wafer, silicon wafer chip that you plug into your board. It's not very helpful though when you're visualizing data. So memory is kind of divided into these cells, right? And right here it's showing these memory cells as kind of 4 bytes. That's what the OX0000 and the OX0004, OX0008, you can see it's incrementing by 4 each time. These are hex values. The OX preceding a number means it's in hex format, which is base 16, right? So the numbers go from 0 to F. 0 to 9 and then A through F. F being 15. That's kind of how hex works, and that's how binary is generally represented, or at least like memory addresses and stuff like that. Memory values. Binary is obviously O's and 1s, but Memory values and stuff like that in the computer and at the machine level are represented as hex values, generally speaking. So if you have 0 to 4, you have 4 bytes because every byte is represented by 1 hex value. So anyway, the cells in memory are often chunked up into individual bytes. Sometimes it's more than that. So for instance, an integer is 32 bits, so that means it's 4 bytes. So these cells right here could represent numbers, very basic integer numbers, or something along those lines. And what happens is, as you start adding variables and all that to your application, those numbers or strings or whatever, they're allocated to somewhere in memory, in one of these cells or several of these cells, depending on the size of that variable, right? And then when you go and you need to use it later, your application will either fetch those from memory somehow, either through the address itself or directly at the cell that it's working on based off of where in memory it's been stored. But the important thing to note is you can visualize memory almost as an array, right? That's a very good representation. That's actually effectively what arrays are under the hood, is just a nice linear way for you to go through these cells of memory. So that's how you can view it. You can think of it like this big array that's allocated for your application, and there's just a bunch of cells, and every time you do something to create data or even invoke a function or whatever, one of these cells is taken up by this memory, and the program knows how to read that or interpret that in the ways that it needs to. So with memory in mind, if you have an integer that's 10 and then another integer that's 50, and then you have a function, there's something called virtual memory that is allocated by the operating system for your application to run. It's not too important right now what virtual memory really is. Just know that it's not actually the RAM necessarily. It's kind of like a fake map over the RAM that the OS knows how to create and keep track of. And every time you create an integer, for instance, or a function even, inside of your application, they're allocated to somewhere in this virtual memory. The code has a specific place in virtual memory. The data has a specific place in virtual memory. And then data like objects, it's special data, has a place in virtual memory as well. And that's behind the scenes mapped to your actual physical memory on RAM, which are those slots. So your virtual memory has a virtual representation of those data slots. And then physical memory has the physical representation of those data slots. And the OS worries about putting those things together. The reason why is your physical memory RAM, there's no way for us to know as the developers what's necessarily in each data slot, right? And the OS will know that. The OS has to know that. Your kernel has to know that. And so what happens is it allocates this virtual memory that looks contiguous. It looks like one giant array to us, starting from 0 up to some crazy-ass number that our maximum allocation is, right? On 64-bit applications, it's huge, absolutely massive. It's 128 gigabytes of memory at once or something crazy, or terabytes or exabytes, or it's huge. But it makes it look contiguous, so when we're writing an application in C or something where we actually need to know memory addresses and we need to know how this stuff is allocated, or even in assembler code or something like that, where you need to know what this looks like, you can without having to worry about the actual physical location of the memory. And the operating system behind the scenes will take that contiguous block of virtual memory and actually map it to the physical places, which could very well be chunked up all over the place, right? They don't necessarily need to be together, but that's not your concern. Now, why this slide is here, talking about virtual memory or physical memory, no idea, but it's here. So when we save something to memory, like a number, for instance, a small number, it might take one of these cells, right? And the application just puts it in one of these cells and keeps track of it through something called the stack, and we'll actually talk about the stack implementation in a moment. And it just puts it there, keeps track of it, and knows how to get it out. If you take two numbers and then you want to console log them, it'll grab both those numbers back out of memory and say, okay, we're going to do an add operation, and then we'll go ahead and log them. So as an application begins to grow and we begin to incorporate larger quantities of information with more relationships, the operations of saving and retrieving memory and all that become more time intensive. So basically there's kind of a linear data problem almost, where as we get more and more memory and we have to go back through that stack or whatever, those memory cells, to find the memory we need, it's probably like a linear time algorithm, I guess, in a very simple sense. Best case scenario, right? But But even so, there's ways we can be more effective about that, and we use things called like data structures to help get around these problems, because data structures can help us manage the memory in a more effective way. And for instance, you might have to be very effective about how you store your memory because you might have limitations. On modern computers, it's very rare. You're probably not going to have any limitations, especially on a 64-bit machine. You can pretty much do whatever you want within reason. I mean, obviously, trying to put terabytes of data in memory at once is a pretty stupid idea, but you'd figure that out real quick. But if you had something like a Fitbit, or if you're doing a Raspberry Pi, or like a Teensy, or one of those small pieces of hardware that are very limited in resources, it's quite possible that you do have serious limitations, and you need to use them very wisely. So you have to think about these things. Very efficient algorithms and very efficient data structures to manage your memory. So if we have something that's more complicated, like say an object, in memory it might look something like this, where we have the name here, like the type or whatever, the animal, the age, whatever it is, and we have some sort of a key value pair that goes to an actual memory cell. So in one memory cell you'll have, say, the age, and the age will point to another memory cell that actually has the value of the age. In one memory cell you might have the name, and another memory cell you might have the string that represents the name, right? Or you might have the start of the string, but it tells you all of the other memory cells that are needed to compose that entire string, right? So you can think of property names and objects as sort of pointers to the actual values in memory. And then your pet itself, the object itself, is going to have its own pointer that then points to the memory addresses of all the properties, right? So it gets very complicated. These structures that we use and we take for granted get very complicated in memory with their memory layouts. Most definitely. So what is a data structure then? It is a way of storing data that can be used to efficiently retrieve, store, or use memory on a computer. So generally, data structure is built upon a very simple primitive type, like a variable or basic numbers or something like that. It's not this big, ginormous object necessarily, or it ends up being that way, but it's composed of very small data types. Most data structures, as they should be, are very unopinionated about what kind of data they operate on, right? They just care that they do something effectively. They have some specific time complexity or space complexity or algorithmic use that they are made for, and they don't really care what you do with them in terms of what you put in them. So an example of a simple data structure is an array, right? What do arrays look like? Well, arrays are really interesting because the way we use an array in JavaScript is functionally very similar to the way we use an array in every language, even C, right? Really low level stuff. You can imagine that arrays are basically just a contiguous block of memory. In JavaScript, it's not really the case at all because of the fact that they can store any kind of data in them arbitrarily. But they're a very simple data structure that are used to store data in blocks and to retrieve the data from those blocks. And again, there's some constant time operations on them. Other cool things you can do with arrays, you can do binary searches over an array, stuff like that, right? Generally speaking, arrays, you can't change how they work under the hood because they're a data structure, but in terms of data structures, they're very simple and very primitive. So they're built into the language usually, and they're not something you would implement yourself. There's actually a need for the compiler, the interpreter, whatever is running your code to provide this abstraction for you into the memory of the computer. In most languages, not JavaScript, arrays are immutable, meaning once you create them, you can't actually change the length of them. For instance, in C#, Java, once you create an array itself, you can't change its size. You can change what's in the array in terms of, like, is the data a 1 or a 2 or a 3 or a 0 or whatever. Or if you have an array of strings, you could change the individual strings at each element in the array. But if you create an array of a length of 5, like this, you cannot change that. So in JavaScript, if you were to do a push on this array, it would go ahead and dump the new element at index 5, right, at the very end of the array. In C#, if you were to call the equivalent add, or, well, there is an equivalent for an array, actually. You have to index it directly based off of where you want to put something in the array. So you can't just do that. There's another data structure that's used in those languages called lists and stuff and sets and stuff like that that are used to arbitrarily change the size of an array. But arrays can't be changed. JavaScript is a special type of array that isn't really an array. It's more like a list. So if we were to push, we'd add it to the end. So how can we add an element to the beginning of an array in JavaScript? Does anyone know that function? Shift. Shift will dump it right in the front. Oop. Again, oh, shift takes it out. Unshift. Ooh, unshift. Yeah, that's what I meant too. Yeah, unshift. So shift actually takes it off the top of the array, and unshift puts it at the top. And what's really happening to this array is something along the lines of this, where it's creating a new array, and then it's kind of like putting all of the other stuff at index 1 through whatever, and then at index 0 it's putting your new item. So this is pretty inefficient as far as algorithms go, because what it has to do is create an entire new array, or it has to take everything and shift it over one element, and then give you a blank cell at the beginning that you can then inject your thing into, right? So you've either got a space problem or a time problem, or both, generally speaking. So you're going to have to go through this entire array, one whole cycle, right, to actually compute this before you can add that first element. So stacks and queues, those are another two really important set of data structures. So stacks are used all over the place. As a matter of fact, your processors, CPUs, use stacks natively to run instructions and hold memory and stuff like that. So stacks, they're similar to an array. There's a major difference, and that is you're only really allowed to access the element at the top of the stack. And stacks are in LIFO order, which is last in, first out, which means you add something in, it goes to the bottom of the stack. If you add another thing in, it goes to the top of the stack. You add another thing in, it's now on the top of the stack, and when you want to retrieve something, you take it off the top. So that push and that pop operation, those are actually stack terms, which are misleading in JavaScript, because in JavaScript, the push and the pop, they just have to do with taking stuff off the end of the array, right? They don't necessarily mean you have this LIFO order that you're going to use. You'd have to do something else to kind of implement that in JavaScript. But stacks are very important in data structure, because LIFO actually ends up being really necessary to do a lot of things. You can reverse arrays with LIFO and stuff like that. But anyway, the important thing with a stack is it's like an array, has an array under the hood, except for your only real operations are to take stuff off the top or put stuff on the top. So we have an empty stack. Say we push a 5 on first, and then push an 8 on. So 5 would be at the base of the stack. 8 would be on the top of the stack. If we push an 11, 11 would be on the top of the stack. Push a 15, 15 is on the top of the stack. Now if we wanted to get 5 off, we'd have to go all the way back through. We'd have to pop 15 off, pop 11 off, pop 8 off, and then we could get to the 5. So we'd have to go backwards in the same order to get the 5 off of the stack. So if we wanted to create a stack in JavaScript, we could do something like this, where we have an array under the hood that represents our items. When you push an element, it lets you it just adds it in. You can go ahead and add it like normal. When you pop an element, you can pop it like normal. When you peek, it'll return whatever's at the bottom. And basically, you have to kind of like reverse how you make the array work, so that you can take stuff when you put stuff in, when you push it in, and it's at the first element in the stack. When you pop something off, you want to take the item from the top of the stack, the last thing that you added in. So queue is reverse of a stack, effectively. Kind of, not really. It's first in, first out. So if you add in a 5, and then an 8, and then 11, and a 15, and you did a shift operation, you'd get the 5, and then the 11, the 8, and then the 11, and the 15 in that order. First in, first out. These are often used for queuing up like operations. So say you had some asynchronous code that needed to run operations in a specific order, you would queue them in the order that they're supposed to run, and then as one is invoked, it's shifted off the queue, right? It's dequeued. So you can do them in the proper order, right? Queues are like lines. First person in the line is the first person out of the line. So grocery store, Disneyland, they even call them queues in Europe and stuff. So again, a queue is not necessarily native to JavaScript. You kind of have to do a little bit of fun stuff to implement it in JavaScript. So you push something to the end and you shift it off the top. Questions about stacks and queues. Now again, I don't expect you to understand the implications of stacks and queues based off of that, but just know that they're like arrays, but they have specific usage, and one's FIFO, one's LIFO, and you can't just access anything in that stack necessarily. So the push and the pop and the push and the shift, those are built into arrays. You could technically use an array to be a stack or a queue without doing any extra work. However, if you wanted to limit how they could access elements in the array, you would need to write a constructor around that. Another common data structure that you'll see is called a linked list. A linked list helps handle some common inefficiencies with an array. So again, think about that array where we want to inject something in the front of the array. We have to shift the entire array over an element, right? And then put something in the front. Well, with a linked list, what happens is you actually have nodes. So you don't have an array, necessarily. You have these nodes that represent values. This node could be an object with property next. There's the next node in the chain, and then a value, right? And what happens is you'll have a node, and then you'll create another node, and you'll say that node is going to be the next node, and then that node will have a next node, and that node will have a next node. And to be able to go through this entire linked list, you'd start from the first element, and then you'd go through each node, and eventually you'll reach a node that doesn't have a next, and that's the end of the linked list. But what they do is they allow you to easily insert and delete things from the top, the first element or the last element. The first element's the most efficient here because you can very easily find the first one, right? Because you'll have a pointer to it as an object. So if you want to, linked lists are like trains. That's a good representation of a linked list. So you have the actual train at the front, and then there's some connection between the other carts on the train. So if we wanted to represent a linked list, for instance, you could effectively have this node class that's just whatever data it's holding, and then a pointer to the next linked list item, the next linked list node. And then you can just get the next linked list node, and then when you eventually get to the end of the linked list, that next node will be null, and then you're done. You're through the linked list. And when we create a new linked list, we effectively just give it some data, and we generate a node for each item in an array. So you could basically generate one off of an array. Let's look at this. Oh, that got a 404. Awesome. Anyway, there are linked list packages that exist out there. For all of these data structures, there will be a package that will exist out there. I can pretty much guarantee you. And again, a linked list is really nice. A simple linked list because that first element, you can easily just replace the first element, right? So we could create a new node, and we could assign the existing linked list to the next of the new node, and then boom, we've inserted it at the front of the linked list. Okay, so these are some really, really basic data structures that are good ones to know that I recommend you study. How's everyone feeling right now? Linked lists are, not linked lists, those basic data structures, even though they are basic, are pretty dense. And learning how to implement them properly in a language unlike JavaScript actually does take a little bit of work, and it's a good exercise. So if you want to pick up another language, C# or Java, or even if you want to go down to the depths of C or something, implementing a linked list, a stack, and a queue is really good exercise for not only getting you used to those languages, but getting you used to those data structures. Okay. So, to the person next to you, let's talk about these data structures really quick. See if we can kind of regurgitate some of this information just to set it into our brains a little bit more. So talk a bit about what data structures are, why they're useful, FIFO and LIFO, what's a stack, what's a queue, what's a linked list, why are they important? All right, let's talk about the next data structure, dictionaries or maps. Which is dictionaries, maps, they're effectively the same thing, just called different things in different languages usually. So dictionaries and maps are, again, linked lists and stacks and queues, arrays, lists, those kinds of things. You'll use those at work. You will. Dictionaries and maps you'll also use, and you've actually used them in this class quite frequently. Dictionaries you'll probably use. This is an incredibly important data structure, which is true. You'll probably use this more than any other data structure that you can think of in terms of other than maybe lists, right? There's a very common situation that we deal with dictionaries. Dictionaries represent a key-value pair. Basically what it is. They have a very efficient lookup algorithm for the key to find the value. And we've seen these. Objects in JavaScript are dictionaries. They are maps. They have a key-value pair. The key is a property. The value is the value associated with that property name. And the key is whatever you can put in that property name, right? So it's a string, it's a number, you can put symbols, you can put all kinds of stuff as object property names, and then you can get an associated value out. Arrays don't solve the problem very, very well of how you print all these pet names, because you have to somehow have two arrays, one to represent the pet and one to represent the name of said pet. So you'd have to have two arrays with the same number of elements, and then you'd have to keep those in sync and just be a real pain in the ass, right, at the end of the day. But using a dictionary or an object in a sense is very easy, because you can just pull off the key value pair, right? You can just print out the name of the property and then the name of the value. So there's actually, other than objects which can act as these maps, there's actually a type called a map that you can use, which has a key value pair, and you just set the key and set the value, and then you can print both the keys and the values, which is really, really nice. Very, very important. Dictionaries and maps aren't necessarily, wow, that's all the slides they had on them. Dictionaries and maps aren't necessarily ordered either, which is really quite interesting. So you can't, you can print them in the order that you add them sometimes, if they're actually ordered underneath the, if they're actually ordered, but sometimes they aren't. Sometimes you'll get them in whatever order, but you always get the keys and the values in the proper order together, right? You'll get the associated value with the key, and that's what's really important. But the nice thing is, again, the best case scenario, why dictionaries are really important, is the best case time complexity on looking up a value is constant time. So it's a lookup time of 1, right? Because of how dictionaries and maps are implemented, they basically calculate this unique key based off of what you give it as the real key, and it can calculate that unique key every time because the input's always the same, and it can find in an underlying array directly where that's stored. So it's a lookup time of 1. Worst case scenario is actually a linear time, but it's very rare that that actually happens in a well-implemented dictionary or map, that you have this linear time. So best case scenario is constant time, so we generally go to it as a default in a lot of scenarios, such as a scenario where we might have a loop that calls that loop again, finding a duplicate or something like that. A dictionary could be a very effective tool for doing that, because you can add something to a dictionary as a key, and then you can see if that key already exists. You've got a duplicate, right? So interesting things like that. They're very, very powerful. If you want to learn more, go ahead and look at the MDN article about it, the developer, Mozilla Developer Network stuff, and read up about them. Implementing them is a little bit more complicated than implementing stacks and queues, because there's a lot under the there's a lot to the implementation to make it efficient and actually work well. So that's also a really good exercise. So I think we're nearing the end here. We have trees and then graphs. Trees are very, very important data structure as well. You won't use them as much in your real work, but they are quite valuable. So for instance, that binary search we saw that we could do with an array, you can also do it with a tree, a node-like tree. that it's kind of like a linked list where it has these nodes, and then you can use those nodes to kind of reference the data in this tree. And they're very effective for doing searching in a very deterministic time frame, right? So imagine you have 1,000,000 elements in a tree. Most trees are generally, worst case scenario, some form of log n or n log n time complexity on a search, an insert, delete, whatever. Because the way a tree works is you'd have a node, a central node, so 11, say 11 is the middle of your array if you had a binary search over an array, and then it actually has references to a left node and a right node. And the way these work is you have this root, and everything smaller than the root is to the left. Everything larger than the root is to the right. So if I needed to say find 9, I would say, okay, the root is 11. Is 9 greater than or smaller than 11? It's smaller than, so we're going to go to the left. Is 9 greater than or smaller than 7? It's greater than, so we're going to go to the right. Oh, we happen to run into 9. So there's two operations there as opposed to potentially searching through the entire array or a linked list or something to find the matching value. So these are really awesome. They have this parent-child relationship, and they kind of branch out to form this logarithmic algorithm that you're going to use for searches and stuff. There are some really complicated trees out there. This is a very simple representation of a binary search tree where it just has a left and a right node, two children, always just two children on a binary search tree. Binary, right? And you can just traverse those child nodes until you find something that matches. And if you don't, you can add it or do whatever, right? So binary search trees, again, they're effectively the most basic form of tree because they have those two nodes and they allow for that kind of logarithmic search. So for instance, this is kind of like what I just explained. This is how a search would work if you're looking for 6 and the root was 11. You go, okay, well, 6 is less than 11, so we'll go to the left. 6 is less than 7, so we'll go to the left. 6 is greater than 5, we'll go to the right. And by that point, you already know that you've hit 6, right? Because 7 and 5, I mean, what else are you going to get? So they're very efficient there, especially as your tree grows in size. The amount of nodes, so if I go back here, what makes it logarithmic, again, was the operations, the search operations are cut in half based off of the number of nodes you have, right? So it eventually gets more and more efficient, because as you add more nodes, it takes more and more nodes to go down go down another level in the tree. So for the first node you add, if you just add a 7 to this, it's the same as a linear lookup, effectively. If you add another node, it's just slightly more efficient. Actually, probably less efficient than a linear lookup, depending on what happens. It could be. You add another node, well then it's starting to become more efficient than these linear lookups, right? And for every node you add, it becomes more and more efficient. And then you can see it. Eventually, there will be a point where adding nodes doesn't really do anything to the time it takes to search through a binary search tree. There are binary search trees in an NPM package that you can try out if you'd like. You can look at the code. I recommend for all of these you go check out the source code because there's a lot that you can learn from how they're implemented. And they're, again, pretty simple as far as data structures go. All right, so graphs. Graphs are a bit more complicated, but they can be a lot of fun too. They're extremely, extremely powerful if you can use some more of the efficient graph algorithms, but sometimes efficient graph algorithms just don't exist. So imagine you had a bunch of cities in the United States, and you wanted to say, model how long it would take to traverse from one city to another, or model how many potential paths there are from one city to another, or something like that. You can do it with what's called a graph. Graphs are crazy because generally the complexity is huge, because there are so many ways you can go from one node in the graph to another node in the graph, and problems like the traveling salesman problem, which I'm sure most people have heard of already, are almost impossible to find nice non-quadratic equation algorithms for solving, because there's just so much going on in a graph. It's literally impossible to find like the most efficient sometimes, you know, depending on what's happening. So example of something you use that uses effectively graphs is like Google Maps, MapQuest, Apple Maps, whatever you use. That is effectively a graph, right? You have one vertex or one node that's going to be like where you started, another node where you ended, and the mapping algorithm might have a bunch of nodes in between that it traverses through to try to find the best path for you. it's just a really great example of where graphs come in handy. Okay, so as far as data structures and all that goes, that's all we really had. Just a bunch of slides, and it was exciting, an hour of slides. There are some exercises that you can look at if you want to with the solutions. Feel free to play with them. If you have more questions, feel free to ask. Otherwise, the rest of the class is for your projects. If you have any questions, anyone have any questions on any of this that we covered? I'll upload them, and I'll put them in the Slack channel too. All right, have fun.